MuSig 2 is uh, probably the most mature of the emerging group protocols. MuSig 2 is a two-round Schnorr signature system. It happens to be convenient for us to begin to experiment with edge identifiers. Um, in order to do that, we'd really like to think about the concept of how do we transmit information securely with GSTP. So I wanted to briefly show a little bit kind of from a Bitcoin-centric perspective, but I think it's applicable for a lot of other blockchains and other kinds of approaches. So to that end, I basically have this page. It's on our developer website with various diagrams in regards to MuSig. So again, MuSig itself is a digital signature that is an aggregation of the digital signatures of n of n parties. So 2 of 2, 3 of 3, 4 of 4, etc. What's really powerful with it is these aggregated Schnorr signatures are always the same size, whether they be a single signature behind them or a multi-signature. Uh, it's also it minimizes the number of interactions as compared to Frost and some other kinds of multi-sig systems. Um, the nonce aggregation has some advantages against accidental introduction of an insecure nonce. And from a privacy perspective, the signature aggregation means that the non-participants cannot tell if the signature is a single sig or a multi-sig. And when used with taproot trees in Bitcoin, this also can be used to enable threshold signing. Um, and this, has other privacy advantages because some of the leaves in Taproot are hidden. Yet the participants can prove they participated in a signature to each other, something that's not trivially possible with Frost and some of the other multi-party computation systems. There actually is now a BIP 327 for MuSig 2, and there is code that has been released to the very well-reviewed SecP 250 libsecp 256K1 library that is used by Bitcoin that just I think day before yesterday became a tagged release. So we wanted to talk about that from GSTP. So Gordian Sealed Transport Protocol basically wraps messages in cryptographic envelopes, ensuring that only the intended recipient can decrypt and access the content. Doing MuSig 2 with just two parties for just an edge identifier or for a single taproot leaf is very easy. But generally, say with taproot, the public, you basically, with taproot, you have a public signature that must be satisfied. And then you have the taproot things, which are all hidden. So if you're going to use MuSig 2 with Bitcoin, it's pretty trivial to make all of the 2 of 2 signatures that are in the Bob and Carol and Alice and Bob and Carol. Those can all be 3 different leaves of the taproot leaf. But generally, in the public part of a taproot transaction, that really should be a 3 of 3. And doing 3 of 3 is hard, especially if you want to do it with 4 or 5. It becomes a larger problem. We believe that Gordian Sealed Transport Protocol can help address the problem of creating in a trustless fashion 3 of 3 and other n of n things. And part of the reason why we think we can do this in a trustless fashion is we have this GSTP-related technology called encrypted state encapsulation, which ensures the coordinator remains trustless by managing the flow of the signing process. So each party will encrypt its state. The coordinator's job is simply to send to all of the parties the encrypted state each step of the process. So MuSig 2 has some requirements and assumptions in order for it to flow properly. It's, says, hey, the parties ought to have secure key agreements. They ought to be resistant to man-in-the-middle attacks to ensure the private encrypted communications. MuSig protocol does not address those in it. Um, you have to be very careful about non-security. The parties must authenticate with each other, which could be a tofu or pre-shared keys or other methods to share the information. And the final aggregated signature is only valid if all the required parties contribute to the final signature. So um, what I wanted to show first was just the two-party multisig, the one that I said is pretty trivial. This is well described in the MuSig BIP. It is also well defined in the MuSig code. So outside of that code, you do have to have this independent authentication and key agreement where session keys are agreed upon, and then you can move directly into the MuSig process. So Alice will send the partial public key to Bob using the session encryption that they previously established. They can then send that group public key to the verifier. Um, Once they do that, they can now do their nonce exchange. When they want to sign something, they can verify the commitments of the nonces, then join into the partial signature phase and verify the partial phase, then aggregate the signed message and send it to the verifier who can verify it. So the MuSig 2 operation is complete for a 2 of 2. Pretty straightforward. 2 rounds, relatively efficient, and very well security reviewed against various kinds of attacks that people might do by playing games with the keys and the nonces. But now let's talk about the 3 of 3. This becomes a little bit more challenging because we really want a trustless coordinator to help us with this. Um, and so we have some assumptions. We want the coordinator not to have access to the sensitive data. We want them not to know what the public keys of the participants are, their nonce commitments, their signatures. Thus, they all have to be encrypted using the very different independent key agreements established between the coordinator and each party. So we definitely also have to have key agreements between the parties that is separate from that of the coordinator, so that they can basically send things to each other without the coordinator seeing any of it. We're using the encrypted state continuation uh, 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 availability feature in GSTP to manage the process of managing the states so that we can have all these different transitions can happen in as far as the server is concerned, in kind of a stateless way. It's the responsibility of the parties when they request the coordinator to do something to return the coordinator's self-encrypted state so that it can go, oh, I see where we are in this process. Let's move forward to the next step. Um, there is some discussion about using some single-use tokens for authentication. That's kind of an open question. But the key thing is the goal of the coordinator is to route message between the parties in a trustless fashion. So we can see the same step 0 here, where Alice, Bob, and Carol are basically requesting session keys for each other. Then they're basically doing the same steps, but now there are 3 parties of the public key collection and distribution of what is the public key that we're going to want to aggregate. Once this is all complete, we can send the group public key to a verifier if we want to do that in advance, or post um, we could use this in a variety of ways. But then we have to do the nonce exchange, the nonce verification, and the signature verification, all using the coordinator to connect all of these different parties together. And when we're done, we have the final signature aggregation moving to the signed message. So this is all on our block page on our page linked at under MuSig and then the MuSig sequence diagram. I think there are a lot of things missing from this. What operations can run in parallel. What places do the UX have to have the user verify these various steps as opposed to automating it. Also, when we're talking, especially in the three-party communication, who initiates and what happens if somebody, despite whatever ordering in the state that we have, decides, well, I need to be the last signer because I'm the CFO and I want Alice and Bob to sign first. So there's some interesting human factor questions when we're talking about multi-party signatures. I'd like to try to address that in future versions of this state diagram.